And we're live.
Okay, so welcome back, everybody. So now we're ready to move on to our second lecture of the second day. And it is my pleasure to introduce Dr. Lisa Miracchi from the University of Pennsylvania. I'm going to start by saying I was really excited about the title. I found particularly interesting: Relevance, Echo Chambers, and Generative Explanation. So really looking forward to that. But before Lisa starts her talk, I'm just going to give you a quick introduction to Lisa. So Lisa Miracchi is an assistant professor of philosophy at the University of Pennsylvania. Her research concerns issues in philosophy of mind, cognitive science, artificial intelligence, and epistemology. She's currently developing a systematic, novel framework for better understanding the distinctive features of mental beings. She's also actively collaborating with scientists, notably the lab of the GRASP Robotics group at Penn University, to test the application of her frameworks to robotics. She's passionate about understanding the world around us and our place in it, putting good beliefs and values into practice, and helping to make academia a more welcoming place for all humans, especially those from underrepresented groups. And this is an additional reason why we're so happy and really honored that Lisa accepted our invitation. So without any further ado, I'll give the floor to Lisa Miracchi for this very exciting talk. Thank you. Lisa, it's all yours.
Thanks so much, Kareem, for that very kind and generous introduction, and thanks for having me here. So as a philosopher, I am interested in helping AI and neuroscience. And recently we've seen a lot of collaborations between AI and neuroscience, as Anil Seth was discussing in our last lecture. And let's ask, how can AI and neuroscience help each other crack the hardest problems? And I will talk about the hard and the easy problems, but we'll get there. For now, I'm interested in a broader range of problems, specifically understanding how we can explain mental and genuinely intelligent features of both biological and artificial systems. So in other work, I call these kinds of properties that I'm interested in psychological agency. So a being that has its own aims and purposes and engages with the world in genuinely purposeful ways. I think squirrels and mice and so on have psychological agency, even if they don't have more advanced forms of intelligence like humans do. And then I'm interested in what I call artificial-minded intelligence. So this is the kind of intelligence that beings with minds have, that includes squirrels and mice and so on, and also humans. And so I distinguish this notion of artificial-minded intelligence that's connected with psychological agency from other notions of intelligence that are defined by other kinds of measures. For example, being able to play Go or chess that some artificial intelligence systems can accomplish. So I think artificial-minded intelligence is particularly interesting, and it should be interesting to all of us, even AI researchers who aren't interested in the mind specifically, because I think it's deeply related to notions of autonomy and flexibility and robustness that AI researchers and roboticists care about. So we're going to be interested in a class of features that I'm going to call mental features that include consciousness, but also autonomy, flexibility, curiosity, planning of the sort that animals and humans exhibit, reasoning, and so on. So our question is, how can AI and neuroscience work together to make progress on explaining some of these features? Okay. So the first thing that I want to do is I want to distinguish between two kinds of questions, and I think it's really important to keep these separate, and often in these discussions we don't. So first, there are what I want to call nature questions. So what is consciousness? So if you were in Anil Seth's talk, you heard that many people think of consciousness as a what it's like property. That's an account of the nature of consciousness. We could also ask, what is agency? What is curiosity? What is reasoning? We can ask whether certain cognitive processes are essentially conscious, whether it's part of their nature to be conscious. And we can also ask, for example, whether there are essential features to reasoning and what those are. In contrast, there are what I want to call generative questions. And my use of generative here, for those of you who are up on the AI literature, this use of generative, be careful, has nothing to do with generative adversarial networks or generative models in that sense. So just as much as possible, try to keep them separate. It's hard to find simple terminology that hasn't been scooped yet. So please bear with me. So generative questions are questions about in virtue of what we're conscious. So these are questions about how neural or computational processes might give rise to consciousness or the capacity for curiosity or reasoning. For example, it might be certain possibility questions. So what kind of possible implementations are there for these mental features? Now, with very, very rough strokes, we can think about neuroscience and AI or robotics as having the potential to contribute distinctive and very important aspects to these questions. So we can think about neuroscience as starting with the existence proofs. So neuroscience tends to start with intelligent or conscious or autonomous systems and investigate their underlying mechanisms. So we'll start with humans or squirrels and investigate what features of their brains give rise to these mental capacities. Whereas in robotics, we can think, or AI, we can think about it as starting with what we can call practice proofs. So we start with basic parts whose functionality we understand, and then we build systems with complex capacities, and we try to see what kinds of capacities we can build. And this includes deep learning and machine learning techniques where we might not be able to fully understand the features that we end up with, but we at least understand the basic neural networks and the learning algorithms that we use. So we can think of these different disciplines as starting from different directions, and it's natural to think that there might be really fruitful places for meeting in the middle. And so one way to ask this question is, how do we integrate insights from these two different approaches? Now, while I'm very optimistic about the potential for and some of the successes of interdisciplinary collaboration between neuroscience and AI, I'm a little bit concerned about what I'll call echo chambers, right? So I think that the way that these interdisciplinary discussions are currently had risks reinforcing certain ideas, not because they're good ideas or they're supported by the evidence or they lead to effective AIs and robots, but because they merely reflect existing overarching research paradigms. So there's a concern that there's a feedback loop where neuroscientists might have a theory that reflects a sort of common underlying research paradigm, and then AI says, well, we have extra support for our view because the neuroscientists are thinking similarly, and then the neuroscientists look back and they say, well, we have extra support for our view because the AI theorists are thinking similarly, and so on. And so I think that we should be very critical when we're thinking about how we take theories back and forth between AI and neuroscience. So while I think this is really important, I think it's equally important to be careful and critical about how we do this. So here is one underlying view that I think is being passed around in an AI neuroscience echo chamber these days. So it's what I want to call computational reductionism. So computational reductionism is the view that mental states and processes can be given characteristic descriptions in computational terms, and so can be implemented entirely by intracranial algorithms. So in a slogan, computational reductionism says that the mental reduces to the computational. So this view is extremely widespread. It has been extremely influential. We can think about such views as thinking of perception as the production of a 3D internal representation, or episodic memory as a certain kind of reconstructive computational process, or decision-making as the execution of an optimization algorithm. These are all examples of computational reductionism in practice. And you can see why it would be attractive for AI and neuroscience theories to talk to each other if they accept computational reductionism, because they have a common vocabulary for talking about mental kinds in purely computational terms. So talking about mental kinds on their own terms is something that kind of drops out of the picture. We can focus on these computational theories, and it makes the problem simpler and easier. But as I hope to show, it oversimplifies the problem in ways that are problematic. So one way to think about what computational reductionism does is that it collapses nature and generative questions about the mind. It says that what mental states are certain kinds of computational states, and what mental processes are certain kinds of computational processes. And so essentially what it does is it collapses the variable scale. If we're thinking about what is the appropriate scale on which to think about mental variables, computational reductionism says that that's the same scale for thinking about intracranial or control system computational processes. And it's an empirical question whether the mental does reduce in this kind of way, whether these two variable scales are the same. And I think they're not. So there are two kinds of resistance that I want to discuss, and I think they're related to each other. The first is what I'll call the objection from semantic relevance, and the second is the objection from consciousness. So I'm going to spend the majority of my time on the objection from semantic relevance. I'll show how my generative approach can allow us to integrate insights from AI and neuroscience without assuming computational reductionism, and so avoid contributing to an unhelpful echo chamber for both disciplines. And then I'll generalize this work to consciousness research and show how it can help us with consciousness research as well. Okay, first, a caveat. So denying computational reductionism does not mean the following things. It does not mean that one denies that the brain executes computations or engages in information processing. In fact, I think it does, and I think that that's crucial to explaining mental features. So denying computational reductionism doesn't deny that information processing plays a huge role in determining mental features, nor does it mean denying that mental processes can be formally modeled. Okay, so I'm also a big fan of formally modeling mental processes, as will come out in this discussion. What it means is that computational or neural variables are at the wrong scale to describe mental states and processes, that we need to keep these models separate and investigate how they relate to each other. So it's a denial of the possibility of a one-one mapping from mental states and processes to computational states and processes. And indeed, I think that understanding the neural or artificial bases of intelligence and consciousness is going to require grasping the complexity of the relationship between the brain or control system, the plant or the body, and the environment. So here's another way to ask the questions that we're asking. Many of you are familiar with Mars' 3 levels of description. There's the computational level, the algorithmic, and the implementational level. And then over on the right-hand side of the slide, I have a sample textbook depiction of various levels of explanation one might have, starting with molecules and going up to social interactions. And so you might ask, where does the computational description fit into our understanding of the levels of existence in the world? Computational reductionism says that the mental is an appropriate subset of the computational level. And we can see this reflection in talking about the mental level as the central nervous system level on the right-hand side. Whereas the generative approach that I endorse says that these two should be kept distinct. We should think about the computational descriptions as lower level with respect to mental features. But as, for example, you can explain the functioning of neural networks in terms of neurons, so you can explain mental features in terms of computational features. Okay. So here's an example to get us to make clear the kind of view that I'm offering, and to make clear that the kind of view that I'm offering is not one that makes the mental special. In fact, I think computational reductionism treats the mental differently from other higher level kinds that we find in nature. So if we take thermoregulation, for example, this is an organism level capacity. It's a capacity that's attributed in the first instance to whole organisms, the capacity to stay within a certain body temperature. And there isn't just one mechanism that's responsible for thermoregulation, either in one organism or across organisms. There are different mechanisms that subserve this function. And moreover, these mechanisms are coordinated so that when one of them is inappropriate to use or perhaps is malfunctioning, another one can step in. So the higher level organism level capacity for thermoregulation is preserved by the coordination of underlying mechanisms. So asking what the mechanism for thermoregulation is a bad question, right? The answer is that thermoregulation obtains in virtue of the coordination of underlying mechanisms in coordination with the environment. Moreover, thermoregulation, this organism level capacity, is a capacity that itself can be evolutionarily selected for. So lower level mechanisms can be selected insofar as they are contributing to this overall higher level capacity. Effective causal interventions might be different at different levels. So you might not be able to, because these underlying mechanisms for thermoregulation are coordinated, you won't be able to interrupt a capacity for thermoregulation just by interrupting one of the mechanisms. These can lead to violations of what's called faithfulness in the causal modeling literature, and other sorts of interesting issues from a modeling perspective. But what I want to point out is that this is part of what leads to this kind of higher level robustness that we'll see. So thermoregulation is a capacity that an organism has that's at a different spatiotemporal scale from its underlying mechanisms. It's because the mechanisms are coordinated in the right way that you have an overarching capacity that is attributable to organisms in the whole instance, and that is robust across a wider range of circumstances than any of the underlying mechanisms. This is related to the neuroscientific concept of degeneracy, where you have different underlying structures that compensate to preserve higher level functioning. There's increasing evidence that degeneracy is widespread in living systems. And we might think that it's really important for thinking about the relationship between computational processes and mental processes. They might exhibit degeneracy in the same way, where you have different underlying computational structures that compensate to preserve mental functioning across a wider range of circumstances. Okay, so what does this all have to do with relevance? So the notion of relevance is one that is famous in the AI literature, especially from the famous or infamous frame problem for artificial intelligence. When we perceive or attend to our world, when we reason about it, learn, action plan, explore, we do so in ways that are relevant, both to what we know and to what we're interested in doing. And so a very interesting question is, how could you build an AI system to understand relevance relations, to act in ways that manifest this kind of understanding of relevance? And those of you who are familiar with the literature, the frame problem for AI in the 80s and 90s resulted in what people often call the kind of death or dark ages of AI. This was a very difficult problem from a good old-fashioned AI perspective. We're seeing, I think, a resurgence of similar problems even with our more advanced AI systems, because although they are they're able to excellently carry out specialized tasks, They don't do well generalizing to new tasks in ways that you would expect if these AI systems could be responsive to relevance relations. They also don't act flexibly or deal with novel environments in ways that animals and humans do, in ways that indicate sensitivity to relevance relations. So how should we think about the problem of trying to either build an AI that grasps relevance relations, or the problem of understanding the information processing and other neural or computational features that underlie biological systems' capacities to grasp relevance relations? Computational reductionism says that we should be able to specify our relevance-related capacities in computational terms, right? Relevance-related capacities are mental capacities in the sense that we've been talking about. And so we should be able to specify those capacities in computational terms. The frame problem, as it's traditionally been conceived, has therefore been conceived as one of building appropriate internal computational models. As I've already suggested, I think that maybe that's not the best way to think about it. What if instead the problem of explaining how systems might be able to grasp relevance relations is a problem of spanning variable scales? What if relevance relations, grasping relevance relations, involves capacities that are at a broader scale than the computational scale? So here's some reason to think that that's true. Our ability to grasp relevance relations is manifested in the kinds of semantically loaded causal generalizations of both common sense psychology, but also scientific explanations. So it's because Neva sees the pelican that she walks to the edge of the beach, right? So here we have a relational characterization of perception, seeing the pelican, and then we also have an action characterization, a characterization in terms of intentional action, walking to the edge of the beach. So in the first instance, these kinds of relevance relations are manifest in these relational characterizations, both of our mental states and our behavior. Moreover, they're typically conscious processes, which we'll return to in a few minutes. And I am afraid of angry panda, so I'm going to try to be mindful of the time, even though we started a few minutes late and have some more to get through. But angry panda, please wait. Okay, so we have these semantic generalizations that reflect this grasp of relevance. Okay, and these characterizations seem to be, at least on the face of them, relational. Okay. Moreover, it's widely accepted that that the semantic contents of our mental states, by everybody, even computational reductionists, it's widely accepted that those contents are determined by our relation to our environment. The question is whether our reasoning is genuinely sensitive to these semantic contents. On the face of it, it is. So it's because Neva sees the pelican that she walks to the edge of the beach. So when we behave in ways that are sensitive to relevance, we're behaving in ways that are sensitive to our mental semantic contents. There's increasing evidence that that appeal to semantic content in this way that manifests grasp of relevance relations is ineliminable from our understanding of the world. So many scientific disciplines make essential appeal to mental contents, from social psychology to economics to linguistics to animal behavior. And I will suggest AI failures to replicate processes that indicate understanding show that content is causally relevant for this kind of intelligent relevance involving behavior. However, computational reductionism is committed to the view that content is causally irrelevant. So by definition, A computer is a formal system whose operations are characterizable in terms of the formal properties of its inputs, its internal functions, and its outputs. Semantic properties, however, are typically significantly determined by your relations to the environment. So although computational states and processes can have semantic properties, those processes don't make a difference to how the system works. So just to clarify what this means, consider this is a hydraulic OR gate from one of my favorite books by Daniel Hillis called The Pattern on the Stone. And if you're interested in basic concepts around computation, I think it's hard to do better than this book. So we can think about, so the way that this works is when water flows in through input A, it depresses the valve and water flows through the output, right? Or water flows in through input B, it depresses the valve and flows out through the output, okay? So if we assign P being true to water flowing in through input A and Q being true to water flowing in through input B, then we can assign P or Q to the output. That's why it's called an OR gate, right? Because it can compute the truth functional connective OR. However, this is dependent, the fact that it computes OR is dependent on our assignment of semantic values to the inputs and the outputs, not to how the system works itself. So for example, if we assign instead P being true to water not flowing and Q being true to water not flowing, then P and Q would be the assignment to water not flowing out of the output. So whether the system computes or and depends on our assignment of meanings to the inputs and the outputs. But note that it doesn't change how the system works. The valve is depressed by the water no matter what. So this is a really important feature of computational systems. It's key to its practical power. It simplifies the problem. You can explain how a computational system works without taking into account its relationship to the environment. But because of isomorphic relations between internal representations and the external world, you can have representations, you can construct complex representations that do reflect some of the structure of the world. So this is an extremely powerful capability that we have to design computational systems, but it comes at a cost. So if you're thinking about mental states and processes as computational, you are thinking about them as symbolically driven, where the causal processes are determined by the internal symbols and not by the semantic properties and not by, moreover, relational properties to the environment. Okay. So one way in which this is problematic is that the functionality of computational systems depends on an isomorphism between the computational system, the symbolic structure of the computational system, and the features of the environment that it is representing. But that connection is going to often be specialized and contingent. So if you change the world, you might disrupt the isomorphism between the internal symbols and the external world. I think that computational reductionism, this focus on specifying mental states and processes as computational processes, reifies this specialization in current AI systems. So I think that we can understand why current approaches can get stuck with specialized systems that can't understand the uncertainties of the world, because we are stuck building internal models that are only contingently related to the features of the environment that they're supposed to represent. If we're trying to build systems that have the kind of robustness and flexibility that animals and humans have with their environment, then we'll have to look at how computational systems can be coordinated with each other and with the environment to give rise to these genuinely relational capacities. Otherwise, they're going to stay brittle and hyper-specialized. Okay. So I do want to be mindful of the time. This slide suggests that it is possibly evolutionarily advantageous to have systems that engage with what's relevant to them for their purposes or for staying alive. It's advantageous to be able to engage with those features directly in ways that are robust. And so you can understand how these relational variable scales could have been selected for evolutionarily. So just like thermoregulation could have been selected for, so having mental capacities at this larger scale, a scale that's larger than the computational scale, could have been selected for. And this doesn't mean that representations don't play a crucial role, just like local mechanisms do play a crucial role in explaining thermoregulation. But what you need to understand mental capacities is how they're coordinated with each other and the environment to preserve these higher level capacities. Okay, so what we need is a way of modeling what I want to call this generative structure. So a way of modeling how these computational processes relate to body and environment to give rise to mental processes. So what I've done in other work is I've generalized the causal difference making literature, where we think about causal modeling not just in terms of making predictions, but in terms of representing what makes a causal difference to what. So just as we can explain what makes a causal difference to what over time, so we can explain what makes a generative difference to what as we move from lower level kinds to higher level kinds. So in contrast with computational reductionism, this kind of view has an asymmetry to it. So we're thinking about the lower level kinds as difference makers for higher level kinds. Our explanations, just like in the causal case, might be context specific. So the explanation for biological mental capacities might be different from the explanation for artificial mental capacities. They also admit of modeling tools and discovery algorithms, which I think is really important if we're thinking about really rigorously modeling generative structure. It's important to be able to apply formal tools. And moreover, this kind of structure, especially for the causal literature, but it also generalizes to the generative case, is that by modeling these kinds of dependence relations, we can understand robust systems level behavior. So for example, a failure of variable B1 might activate another mechanism B2, preserving the higher level functioning, right? And so part of what we should be interested in doing is understanding how the various coordination of these mechanisms preserves these robust systems level behavior. So to get a little bit more precise, what we need is to keep separate our model of mental features, which I've called the agent or emergent model, from the generative model, from the basis model, which is the model of underlying neural or computational features, including some features of the body and the environment. And then we have the generative model, which models dependence relations between the agent or emergent model and the underlying features. And so in this way, we can have rigorous models that don't collapse the mental features onto computational or neural features. Okay, so just very briefly, I want time for questions if we can, but let me just say that we've already started to apply this kind of framework for thinking in robotics. So a recent paper with Sonia Roberts and Daniel Kodacek and I applied this kind of generative framework to thinking about Gibsonian affordances in robotics. So we showed that you could ask as an empirical question, what representations a system needs in order to exploit Gibsonian affordances. So there's often an assumption that one needs to represent Gibsonian affordances in order to exploit them. And we show that that's not always correct, and that by distinguishing basis models and emergent models and providing generative explanations, we can turn this into an empirical question. So lastly, I'll just say a few things about consciousness research. So on this kind of approach, I think we should stop trying to, oh, I know, Angry
Lisa,
Panda.
you need to wrap up now. You have
Okay,
1 minute,
1
okay?
minute. Thank you, Angry Panda.
Yeah.
So according to this kind of generative approach that I advocate, we should stop trying to define consciousness, especially in neural or computational terms. Neural processes can generate consciousness even if consciousness isn't a functional property. And I explain elsewhere why I think this can help us get a handle on the hard problem of consciousness. More importantly, for our purposes, I think the hard distinction between, or the sort of firm distinction between what are called the hard and easy problems of consciousness, where the hard problem is explaining why there's something it's like to be conscious, whereas the easy problem is the problem of explaining the functional roles associated with consciousness. These problems are no longer completely separate because we're not committed to a kind of reductionist view that says that the functions associated with consciousness can be specified independently of consciousness. So when I described Neva walking to the edge of the beach because she sees the pelican, that is typically a conscious mental process. And we can include conscious descriptions of our mental processes in our agent models without loss of rigor, because we're not defining one of the variables in terms of the other. We're just we're modeling dependence relations. This is really important because I think it helps us get a handle on the hard problem of consciousness. As people have been suggesting, we might be able to dissolve the hard problem of consciousness. My suggestion is that if we can get a grasp on understanding how systems manifest sensitivity to relevance relations, how they're genuinely semantically sensitive, we will get an explanation of consciousness for free. Many of these intelligent behaviors are, I think, essentially conscious, and we'll be able to understand the neural and computational basis for them by understanding how they generate this higher level, essentially conscious behavior. Okay, I will end there and thank my research group, Mira, as well as COD Lab and GRASP Laboratory. So thanks, everyone.
Thank you, Lisa. That was outstanding, and it lived up to the expectations of that wonderful title. So thank you again for that. We do have a couple of minutes for a couple of questions. We are 5 minutes late in our schedule, so we'll take a few questions, and then we'll have time to elaborate more later in the panel, of course. So I'm looking at the questions that have been upvoted here by the audience. The question that has been upvoted most is the following. It's a question by Nicola Wilkinson. So to what extent and in what ways does taking the anti-computational reductionist view you described create difficulties in working or discussing with people who are pro?
Thank you. Yeah, thank you for asking this question. I am, as I hope is evidenced by the talk, I'm very committed to interdisciplinary collaboration, and I think that it's possible to have collaborative discussions even with people who are pro-computational reductionism. What I think is really important is that all of these different methods for thinking about mental processes, be they predictive processing or theories of consciousness like information integration theory or global workspace theory, they're all, for me, aspects of thinking about basis models. So I think that the insights from predictive processing and other computational theories can help us understand, have a better handle on basis models. Now, one upshot of the generative approach that I'm recommending is that we don't necessarily have to choose between them. So it can be a both and situation where in some instances, certain computational processes are the ones that are important for understanding the mental feature we're interested in. And in other cases, it's other kinds of computational processes.
Makes a lot of sense. Thank you so much. I'm going to move quickly to the next question. This is a question by Janek Hashka. Wouldn't an embodied AI system get a sense of relevance via its body and the task given to it?
Yes.
That's a fun question.
So, yes. So thank you for this question. I think that embodied AI is the way to actually build AI that has genuine mental capacities. And it's not because I think embodiment is necessarily tied to intelligence or mental capacities, but because I don't see another way practically of generating this kind of integration with one's environment, right? So it's via the body that we can span these variable scales and have whole systems that are genuinely causally related to distal features of their environment. However, such an embodied AI would need to be built differently. Current robotic systems tend to reinforce this kind of causal joint between the control system and features of the body and the environment. Whereas on my view, we would be interested in implementing causal coupling on many different levels between the control system and the body and the environment.
Okay, well, as I said, there are many more questions. I see there's a super interesting question by Jess, but I'm guessing I read the question, it looks like that will take you more than 30 seconds to answer that one. So we don't have that time, but I really hope we'll get back to it. And again, all the questions we'll have a log of them, so we can also get them later on. So in the interest of time, I'm just going to thank you once again, and bringing in also this philosophical perspective onto the questions of the neuro-AI intersection, looking into consciousness. Philosophy has not been present enough in this debate. So we're really so happy that we managed to get this done in this session with you, and we'll get back to this question again later on in the panel discussion. So join me again, please, everyone, in thanking Lisa for this outstanding talk. The next one up is going to be a talk by Joshua Benjo. So we'll see you in a few minutes.
Thank you, everyone. See